Okay, welcome to
Every
Carve
time we
Day.
take the circle.
We're gonna go ahead and look at the unit circle today. It is closely related to our table and Santa Claus idea. Usually students will use one or the other. They'll pick the unit circle and memorize it and reproduce it on the test and quizzes and then pick the numbers off. Or you'll continue with the table and Santa Claus. Usually from my teaching in this course, 60% more or less use the table and Santa Claus, and 40% will use the unit circle. It's up to you. I will not give you the unit circle to use on the test. You will have to produce it from memory. But I'll show you how to come up with it in an easy way. Let's talk about the background behind the unit circle. We're going to start with, it's a unit circle because it's really a one unit, meaning the radius is equal to 1. And we're going to remember that we have an x, y, and an r. R is the radius, and then I have my theta, which is my angle. That has not changed. One little piece of information is that your theta in radians is equal to your arc length divided by your r. And when your r is 1, you're going to see that your theta in radians is just equal to the arc length. So if this is a length of 1, your theta is equal to 1 in the unit circle. This is something we're not going to use too much, but it's just one point of the unit circle. We're also going to get into what your x and your y coordinates are on the unit circle. Your x, y coordinates are going to be the same thing in terms of cosine theta, sine theta. This is important to know. And the reason why it's true is because if I were to think about what is the cosine of theta, I know it's going to be x over r, adjacent over hypotenuse. But you know that your r is equal to 1, so in this particular case, it's just going to be x over 1, which is x. That's how I know that this x is equal to the cosine theta. For the same reasoning, the y is equal to the sine theta. You could just think about it in terms of the definitions. Cosine theta is x over r. Cosine goes with x's, y goes with sines. So it has to be in that order. When I'm given any point on the unit circle, it's always going to be in the order cosine theta, sine theta. All right. Also, you know this Pythagorean theorem is going to be x squared plus y squared equals r squared. The next slide I'm going to show is going to be the unit circle. And it actually looks really scary, but once you get to use it, it becomes a lot more friendly. So we're going to carve this up and make it into a more friendly way of using this by trying to reproduce it. So we're going to look at this in parts instead of the whole thing and try to make sense of it. I won't let you use the paper copy, but if you do want to on the test, you can write this down from memory on a separate sheet of paper. And I'm going to explain all the different components of this in the way that I think is the easiest way to remember. So let's first of all think about the ordered pairs at the intersection of the axes and the circle. I know just the angles I'm dealing with 0, 90, 180, 270, and 360. That we've worked with before, and I also know them in terms of radians now, pi over 2, pi, 3 pi over 2, and 2 pi. So the angles are pretty straightforward. Secondly, I'm going to think about them in terms of the angle between. Now look at your degrees, 30, 45, 60. These are all of your reference angles. I'm going to use each of those to come up with all my other angles. And I'm going to look at the 180 and the 360, for example. 180 plus or minus 30 gives you 150 and 210. So I'm going to add, subtract my reference angle to 180 to come up with those other angles, and I'm going to subtract it from 360 to come up with 330. 45, I'm going to subtract it from 180 to get 135. I'm going to add it to 180 to get 225, and I'm going to subtract it from 360 to get 315. So all you're doing is adding, subtracting the reference angles to come up with the other angles. Same thing for 60. For the radian measures, you're going to do the same exact thing. Pi over 6, when I go to pi over 6, I'm going to subtract pi over 6 from pi, and I'm going to get 5 pi over 6, and add it to pi, and I'm going to get 7 pi over 6. Same thing on this one, 2 pi minus pi over 6, and I get 11 pi over 6. So that's just adding, subtracting reference angles can get you all of the degrees or radians inside of the circle. Let's go to outside the circle now. Outside, so the first thing is going to be reference angles, and what you're going to do is add and subtract from pi or 2 pi, let's say 180 or 360. The second thing we're going to do is look at these numbers outside, and you know the intersections. But let's take a look at the more specific ones. If you remember the table, and on the table you're looking at sine theta, 0, 30, 45, 60, 90. And you're going to remember that you have 0. Sine 30 is the one that I think is easiest to remember as 1/2. Then you can pretty much fill in the other ones. When you go on the sine theta from left to right, you're going to be doing the same thing here all the way this way. It starts at 0, it goes to 1/2, 1 over radical 2, radical 3 over 2, and 1. It's your y value. Remember that your sine theta goes with your y. That's what we learned in the previous slide. So one thing you really need to know here is your x's is cosine theta and your y's are sine theta. X goes with cosine theta, y goes with sine theta. All right, so when I'm looking at the sine theta on these degrees in the first quadrant, I'm really looking at my y coordinate, and that's why I'm looking 0, 1/2, and getting those values. Then what I could do in the first quadrant is just go in reverse. Come back from 0 to 1. That fills out the whole first quadrant. And once you have the first quadrant done, now it's a matter of reflecting and remember which ones are positive and negative. If I reflect the first quadrant over to the second quadrant, look what happens. It's the same values. You line them up, except you're dealing with positive or negative. Here you're dealing with a negative x and a positive y. So your signs have to be negative, positive. And once you get them reflected over to the left, you then take the whole top and reflect them down, and then just put in the right signs on the numbers. So really, it's not too bad if you make it into pieces and do it one thing at a time. All right. Today, what your job is going to be is to forget about the table and the Santa Claus for now, and just get the answers off of the unit circle. So the assignment is actually pretty easy. We're going to have another concept because it is a pretty easy concept. If you're given these problems now, 6 trig functions for 5 pi over 3. Look at how easy this problem is. I'm going to go back to the unit circle, 5 pi over 3. I'm going to go right to 5 pi over 3, and I know that this right here, your x is the cosine theta, your y is the sine theta, then the tangent theta is going to be y over x. By its definition, y over x is negative radical 3 over 2 over 1/2, which becomes negative radical 3. So that's how you're able to fill in the chart pretty easily. 1/2 negative radical 3 over 2. And so you're going to have those values. And then the same thing for the other one is just the reciprocal of those values. You can see that it becomes pretty quick with unit circle. Some students will take a piece of paper, fill up a whole unit circle, and then just pick off the answers when you need them. But this isn't going to solve all of your problems, because next chapter we're getting into graphing, and then then after that it's going to be identities, which involve all these substitutions. Let's take a look at this problem, and it says, what's theta now? If you know that the sine of theta is equal to a negative 1/2, what does your theta equal if you know that theta is between 0 and 2 pi? And so you're going to look at the unit circle, and because its sine theta is negative 1/2, you're really looking to see where y is equal to a negative 1/2. Where y is equal to a negative 1/2, you go back to the unit circle, and you're going to really see that negative 1/2 for your y really cuts through this right here. That's where your y is equal to a negative 1/2. So what are the angles that create that y of negative 1/2? Well, one angle is going to be 7 pi over 6, and the other one is going to be 11 pi over 6. There are two answers when you're doing this. So that means that this is going to be theta is equal to 7 pi over 6 and 11 pi over 6. We're going to be getting into graphing, and that would mean that for these two angles, you're going to have the same y value, which means that, you know what, when you're graphing down here, it's going to be kind of like this, where this is a negative 1/2, and you're going to have two answers for your y as you go along for your different x's. So this would be like 7 pi over 6 would be your angle, and this would be 11 pi over 6, and it's going to come back around. So that's just, we're going to get into this a lot more. It's just an idea for you to think about when, so you've seen it just once before. Let's go to the more confusing topic of today, and that's going to be odd versus even functions. And odd versus even functions, this is one question that could be on your next test. It's one of the topics that I chose to focus on in terms of having you remember it, and it's a concept that will make your life easier in the long run. Knowing the definition is fairly straightforward. That's just knowing what the definition is, and then understanding that sine theta or cosine theta is even or odd is the other idea. And then the third idea is why it's true. So you really have three concepts here. This would be the definition. This right here is going to be the trig function if it's odd or even. And then the third idea is why it's actually even or odd. This is the topic where you have to really think in order to follow. And I think if you go back and look at it, you're going to have to study it in order to reproduce it, just because it's a little bit out there. Let's take a look at even and odd functions first of all. And what I want to do is talk about what is an even function, what is an odd function, and then what I want to do is talk about why the sine and the cosine are even or odd. Again, we're doing this to make my life easier down the road with proofs and identities. So this will come up not very frequently, but it will come up. What is an even and odd function? First of all, even function is where I take an f of x, some function, and say, okay, if I put in a negative x for x, then I'm still going to get f of x. I'm going to get the same exact function. For example, if I had an equation where f of x is equal to x squared, if I put in a negative x in for x, I'm really going to get a negative x squared, which equals x squared. Negative x times negative x is x squared. This right here, f of negative x, is the same exact thing as f of x. They're equal. So that's why I know that f of x is equal to f of negative x. They equal the same exact thing. Now, if this is true, whatever function you have, this is just one example, but if it's true that if you put in a negative x and for x and you get the same result, the characteristic of that function is that it's an even function. That differs from an odd function. An odd function is where we're going to say that f of negative x is equal to a negative f of x. Well, let's think about an easy example where that's true. If I were to think about f of x is equal to x to the third power, and I put in f of negative x, I'm going to have negative x to the third power, which equals a negative x to the third power. I'm just throwing in a negative x in for my x, and then I'm going to actually cube it. I'm going to multiply negative x times negative x times negative x cubed. Now notice what's different, and it's kind of subtle here, is f of x is equal to a negative x is equal to x cubed. But if this were a negative out front here, if I were to say, okay, instead of x to the third, I'm just going to put a negative out front here, I could actually multiply both sides by a negative, and you're going to see if I did that, my negative f of x equals negative x cubed, and my f of negative x equals negative x cubed. These two are exactly the same, which means these two are exactly the same. And that's the definition of an odd function. F of negative x equals negative f of x. They yield the same exact negative x cubed in this particular function. Now there are tons of infinite number of functions out there. Some of them have even characteristics, some of them have odd characteristics. Some of them don't have either characteristics. Okay, this is just a special way of labeling a characteristic of a tree function or any function. Now, that's the first part. That's the explaining what that means. If I didn't know what that means, then I can't really go any further. So I hopefully have a better idea of what this means. Now, I want to evaluate sine and cosine and see if it's even or odd. I'm going to use the unit circle to do this. Notice your xy is the same thing as cosine theta sine theta. That was from before. If I were to go theta here and a negative theta there, notice what happens very quickly. If I were to look at this angle, I get my x is equal to cosine x. Since you're still dealing with a positive x, your x is equal to cosine negative x. Since this x is the same thing as cosine theta, and this x is equal to cosine negative theta, it's the same thing. Cosine negative theta and cosine theta both give you an x from up above, and therefore it's going to be even, because that's what this says. F of a negative x equals f of x. Cosine negative theta equals cosine theta. Cosine is an even function. Odd, let's take a look at the odd function. Sine theta equals y, but down here it equals negative y, which means your sine negative theta equals negative y. And this is where it gets a little bit strange. Negative y is the same thing as negative sine theta, which is right here. Multiply both sides by negative, and that's why it has a definition. Sine negative theta equals negative sine theta, which tells me it's odd. Subtle, hard to follow, often is the case. Students have to look at this a lot more than once or twice. All right, you've got the remaining 2 minutes to think about what just happened there, and hopefully you don't smash any pumpkins over the holidays.